Hello everybody, I am Ashok from AKB tutorial. So in this channel we are discussing various topics related to mechanical engineering. Today we are going to discuss about that is shear force and bending moment diagram part 2. So in part 1 we have discussed the basics of shear force and bending moment diagram, and today we will learn the basics of cantilever beam, how to solve the problems. So let us start. So a cantilever beam. So we know what is a cantilever beam. So in last video we have discussed what is a cantilever beam. A beam whose one end is fixed and other end is free, that beam is called a cantilever beam. The beam whose one end is fixed and other end is free is known as cantilever beam. The beam may be loaded with a point load or any other kind of load. So we will start with a point load. Let a load capital W is loaded at the free end, and the length of the beam, let the length of the beam is L. Okay. So as soon as the load W is loaded at the free end, a reaction will develop at the fixed end. Let the name of the beam is AB. So we will give the reaction as RA. So RA is the reaction will develop because the vertically upward load and vertically downward load will be equal as per the static equation, because beam is in equilibrium condition. So for this, so W will be equal to RA. So we can write directly RA is equal to W. Also, this W load will create an clockwise moment. So an anti-clockwise moment also will develop here at the fixed end. So we are giving the name M0 is the moment developed at the fixed end. Because of this moment, so what is the moment produced by W about the fixed end is given by W into L. So force into the perpendicular distance from the load to the moment center. Okay, so M0 also will be equal to W into L. So thereby the beam will be in equilibrium. So from this we have got RA, the vertically upward reaction force will be equal to W, and the moment at the fixed end will be equal to W into L. Now we are going to see the shear force and bending moment diagram. So for shear force diagram, so consider a section XX at a distance X from free end. So we are considering a section at a distance X from free end. Okay. Now shear force at this section. As per the definition of shear force, the algebraic sum of all vertical loads acting to one side of the beam. So we are considering the right side of the section. What are the vertical loads acting? Only W load is acting. So shear force at XX we can write that is W. Also we have seen the sign convention. If this is the section and right side load is acting in downward direction, then that will be the shear force will be positive. So that means we can write shear force at XX is equal to W, that is positive. So if the load is acting downward at the right side of the section considered, then that shear force will be positive. Okay. Now we will slide this section. This is the section XX. We will slide this section to point B. So we will get shear force at point B. Now at point B, slide this section up to point B. Point B means 1 point left to point B. 1 point left. So if we see how much load is acting, vertical load, right side of that section, only W. So that means shear force at point B also will be W. That is also positive. Now slide the section to point A. So we will get shear force at point A. What is shear force at point A? Point A means 1 point right to point A. So if we see 1 point right to point A, what is the shear force? Total vertically downward load right side to the section. So that is also W. So we are writing it is W. That is also positive. So that means first we will find that equation of shear force at section XX, that is algebraic sum of all vertical loads acting to one side of the section. That is W. We have got W. Then slide the section to point B and then slide the section to point A. It will give shear force at point B and shear force at point A. Now with this information we will draw the shear force diagram. Now to draw this diagram, just take the okay, we have drawn the extension line. Draw a baseline. So let this is the baseline. This is your baseline. Okay. Now shear force at point B, at this point it is W. Say with some scale, say this indicates W. And shear force at A, it is also W. So with the same scale you measure this distance W. And the variation here no variables are present, so variation is not there. Shear force at point B W, shear force at point A is also W. If we take any intermediate point, shear force also will be W. So that means there is no variation at all and shear force will be constant throughout. So this will be the shear force diagram. As the shear force is positive, so we will write here positive and put the hatching marks. So this completes your shear force diagram. Now we will move to draw the bending moment diagram. So before drawing the bending moment diagram, so we will calculate bending moment at section XX. So what is bending moment at section XX? As per the definition, bending moment at section XX is the algebraic sum of moments of all vertical forces acting to one side of the section. So if we consider the right side, so bending moment at section XX is W into this distance. That distance is X. So we can write W into X is the bending moment at section XX. Now similar way we will slide the section to point B. So we will get, if we slide the section to point B, X value will be 0. X value will be 0. So thereby the bending moment will be W into 0. That is bending moment at section B becomes 0. Now we will slide the section to point A. Then bending moment at section A, that will be equal to W. When we will slide the section to point A, X is measured from this point, from 3 end, so X will become L. X will become L. So that means bending moment at point A will be W into L. With this information, we will draw the bending moment diagram. So we have seen the sign convention. So in the basic, means in last video we have seen the sign convention. So as per this, the sign convention will be negative. Okay. So this information we will draw here, so that this is the baseline. This is the baseline. What is? This is the baseline. Now at this point shear force is 0. At point B shear force is 0. So mark this point, and at point A shear force is W into L. With some scale draw W into L value here. So W into L. So this indicates W into L. Now we will see the variation. Bending moment with section varies with x. So variation is linear. Variation is linear. Linear means straight line variation. So we will draw a straight line from this point to free end to fixed end. So this will be the bending moment diagram, and as the diagram is negative, so we will put here negative and put the hatching mark. Okay, this is all about the bending moment diagram for this type of loading. So when W load is acting at the free end of the cantilever beam, then shear force diagram will be a rectangle. This is the multi-choice question. So this diagram is a rectangle. Shear force diagram is a rectangle, and bending moment diagram will be a triangle. Okay, and also from here, from bending moment diagram, it is seen that bending moment at free end is 0 and bending moment at fixed end is maximum. So this is also multi-choice question. For cantilever beam, the bending moment at the fixed end will be maximum, and shear force diagram will be a rectangle for point load acting at the free end. Now we will see the next problem, that is cantilever beam is subjected to various point loads. So to number of point loads. Okay, so this is the problem. So if we draw the diagram, so for solving the problem, so it is better just divide your page into two parts. In one part we will draw the diagram, another part we will do the calculations. Okay, so first we will draw the load diagram. So the cantilever beam, this is the cantilever beam. The beam is under load, multiple point loads are acting over the beam. Say W1, W2 and W3 are the loads acting over the beams. W1, W2 and W3, 3 point loads are acting over the beam. Let the length of the beam, length of the points where the loads are acting, say this distance is given by L3, this distance is given by L2 and this distance is given by L1. Okay, 3 loads are acting at various points, so the distance from the fixed end is given L1, L2 and L3. Okay, now we have to draw the shear force and bending moment diagram for this condition. Now consider a section XX here. So XX section we have considered at a distance x from free end. What is the distance x from free end? So we have considered a section XX at a distance x from free end where W1 load is acting. Okay, so so shear force at XX. So as per the definition, we know the algebraic sum of all vertical loads acting to one side of the section, say right side. So at the right side of XX section, what is the load acting? Total vertical loads, that is only W1. So shear force at XX is W1. We will write here. Now we will give the name. Say AB is the beam and this point is C, this point is D. Okay, no problem. We have given the name. Now slide the section to point B. If we slide the section to point B, so shear force at point B will be W1 only, because the vertical load acting to right side of the section is W1. Now slide the section to point C. So we will get shear force at point C, that is also will remain W1, because right side of this section total vertical load is acting is W1. So it is W1 only. Now take another section here. Say Y section, which is at a distance Y from the free end. Y from free end. This distance is Y from free end. Now we will find shear force at YY section. So now shear force at YY section, the algebraic sum of all vertical loads acting to right side of YY section. What are the loads? W1 plus W2. So two loads are acting right side of section YY. So it will be equal to W1 plus W2. Now slide the section to YY section to point C and point D. So we will get shear force at point C, that will be equal to W1 plus W2, because when we slide the section to point C, it is just 1 point left to point C, and slide the section to point D means 1 point right to point D, that is shear force at point D, that will be also equal to W1 plus W2. Okay, now take another section here, that is ZZ section, which is at a distance Z from free end. Okay, so we will find shear force at ZZ, shear force at ZZ section. So shear force at ZZ, what will be the shear force at ZZ? It is the sum of algebraic sum of all vertical loads acting to right side of section ZZ. So that is W1 plus W2 plus W3. So we can write W1 plus W2 plus W3. Now slide the section to point D. So we will get shear force at point D, that will be equal to W1 plus W2 plus W3. Now slide the section to point A. So we will get shear force at point A, that will be equal to W1 plus W2 plus W3. So all the loads, all the shear force what we have got, that is positive in nature, because right side load is acting in downward direction, so positive. So at this section also right side load is acting downward direction, positive. At this section also, if we see, all the loads are acting downward direction, that is positive. At this section also it is positive. So that means all the shear force are positive. So with this information, so draw the extension line and we will draw the shear force diagram. First you draw a baseline. So let this is the baseline. So we have drawn a baseline. At this point, what is the shear force? Say W1 with some scale. We are marking this one as W1. This height is W1. And this will remain same up to this point. So that means this will remain constant up to this point, up to point C. Now you can see at point C it is W1, again at point C it is W1 plus W2. So at this point the shear force will vary, and that will remain constant up to point D. So this is point D, and again at point D shear force will change, and that will be W1 plus W2 plus W3. So W1 plus W2 plus W3. So W1 plus W2 plus W3. So at the fixed end. Now this is the shear force diagram. So here it is W1, here it is W1 plus W2, this height, and this height is W1 plus W2 plus W3. So here you can show it. And all shear force are positive. So we are writing positive and put the hatching mark here. Okay, this will complete your shear force diagram for the beam when the beam is under multiple point loads. Okay, now we will go for bending moment diagram. Now to find the bending moment diagram, first we will consider the x-axis section. So bending moment at x-axis, so we will find the equation. What is bending moment at x-axis? Now algebraic sum of moments of all vertical forces acting to one side of the section, say right side of this section. So right side, what is the force acting? W1. So W1 into x. So it will give W1 into x. Okay. So now slide the section to this point and slide the section to this point. So we will get, so this distance we have considered L1. Okay, no problem. So bending moment at section B. Bending moment at section B. What will be? X value will be 0. So W1 into 0. So that will be 0. Now we will find bending moment at point C. Bending moment at point C. When we slide this x-axis section to point C, what will be the x value? X value will be this one. This one means total distance is L1 and this distance is L2. So it will be W1 into L1 minus L2. So whatever is coming, whatever value is coming, W1 into L1 minus L2, because at this point, what is the x value? When we will slide this section to this point, so x value will become this. So x value will be this length minus this length. This length is L2 and this length is L1. So L1 minus L2. Now we will find bending moment at YY section. Bending moment at YY section. So where is the YY section? This is the YY section which is at a distance y from free end. Okay. So we can write W1 into y plus W2 into this distance. We will come W2 into, what is the distance? So this is the distance, W2 into this distance. So total distance is y and this distance is L1 minus L2. Total distance is, so we have to take moment about this section. So W1 into y, no problem. So W2 will give the moment about this section. So we have to give this distance. What is this distance? So this is the y value, y minus this distance, y minus this distance. So we can write y minus, that will be L1 minus L2. L1 minus L2 is the distance. Y minus L1 minus L2. Y minus L1 minus L2. Y minus L1 minus L2. Okay, that is clear. Y minus L1 minus L2. So this distance is y minus this distance. Y minus this distance, then we will get this distance. This distance is how much? L1 minus L2. Okay. So y minus L1 minus L2. Okay. So just continue bending. So slide the section to point C. So we will get bending moment at point C. What is bending moment at point C? At C point y value will be L1 minus L2. Y value will be L1 minus L2. So this will cancel. Y value will be, so it will be W1 into Y plus W2 into Y minus L1 minus L2, L1 minus L2. So Y value will be L1 minus L2. So L1 minus L2 minus L1 minus L2. So that means this will be 0. This will give 0 value. This will give 0 value. So it will be W1 into Y. Okay. So this value and this value will be same. So at point C, here at point C, Y. Okay, Y value. So okay, put. Okay, it is correct. W1 into Y. So you put the value of Y. W1 into L1 minus L2. So this value and this value will be same. Right? Now we will go for section ZZ. So bending moment at section ZZ is equal to. So ZZ section is at distance Z from the free end. Z from the free end. So W1 will give the moment W1 into Z. W1 into Z plus for W2 what will be the moment? W2 into this distance we have to multiply. That will be equal to W2 into Z minus W2. Z minus this value. This value is L1 minus L2. L1 minus L2. So this put in bracket plus W3 into Z minus. So let us see W3. So we have to give this distance. So W3 into this distance. What is this distance? That is Z minus this distance. What is this distance? This distance is L1 minus L3. L1 minus L3. Put this one inside the bracket. Okay. So this will be the value. With this information, we will draw the bending moment diagram. All these are negative value, negative bending moment. So as per the sign convention, all these are negative bending moment. And for this, to draw the bending moment diagram, draw a baseline first. So this is the baseline. Now after baseline, go to point B, where point B will give 0 value. Okay, bending moment diagram is 0. Now you go to point C. What is the value? At point C is W1 into L1 minus L2. With some scale you measure this height. So you will get this point, and you just, the variation is with L1 minus L2 bending moment. Variation is with X. So that means linear variation, straight line variation. So put this diagram. So from point B to C the diagram is made. Okay. Go to YY section. Bending moment at C is equal to same bending moment at D. With the same scale you just draw this height. What is this height? Bending moment at D, bending moment at point D. So we have not calculated at D. Okay. Okay, it will be same value, it will come. Okay, say it is coming this one, and ultimately slide the section. Okay. So we have not slide it. Bending moment at ZZ, bending moment at YY. So we have slided to section up to C. So we have got this value, and when we will slide to D, so that time it will give some value. Okay. Okay, at now we are calculating bending moment at point D. What will be the bending moment at point D? So when we will slide this section YY, to D point, so y value will be this one, y value will be L1 minus L3. So is equal to W1 into L1 minus L3, W1 into L1 minus L3, okay, plus W2 into bending W2 y instead of y, L1 minus L3 minus, it will be L1 minus L2, L1 minus L2, okay. So this will come, so with some scale you just mark here this value. Now go to bending moment at D point, so this also will be equal to this value and this value will be equal, okay, because this one will be 0, okay. When we will slide the section ZZ to D point, now you slide the section to point A, so it will give bending moment at point A. So in this equation, ZZ equation, at bending moment at point A, Z value will be L1 is equal to W1 into L1 plus W2 into Z value will be L1 minus L2 plus W3 into Z value L1 minus L3. So L1 minus L3. So this will be the value. So with the same scale, you just mark here, say this is the point we are getting. So this value will be equal to the shear force at point C, and this value it will be equal to the shear force bending moment at point D, and this value will be equal to bending moment at point A. Now all the variations, the first variation with X, second variation will be with Y, linear variation, and third variation will be with Z. So with Z, in this equation Z is there, so linear variation, so that means straight line variation. So just join these points, okay. So this will be the bending moment diagram when the cantilever beam is under multiple loads, and put here negative and put the hatching mark. Okay. Now we will see the next problem, that is if the cantilever beam is under subjected to uniformly distributed load only uniformly distributed load is acting over the beam. So for that case, what should be the shear force and bending moment diagram, we will see. Now this is the cantilever beam. The beam is under uniformly distributed load. What is uniformly distributed load? The load is evenly distributed over the whole span of the beam or part of the beam. So that kind of load is called uniformly distributed load, and the magnitude of load will be given in the question. Say here it is given W per meter length, and length of the beam, say it is L is the length of the beam, and total load acting on the beam. So we can write total load on the beam. This is coming as a multi-choice question. Total load on the beam is equal to W into small w into L. So we have considered that small w is the load, uniformly distributed load acting over the beam. Okay. So total load per unit length is W. So for L length it is W into L. Now for drawing the shear force and bending moment diagram, so give the name of the beam as AB. Now consider a section XX at a distance x from 3 end. So we have considered a section x from 3 end. Now we'll write the equation of shear force at xx. What is the shear force at xx? Algebraic sum of all vertical loads acting to one side of the section. So right side of the section, total vertical load acting right side of the section. For this x meter length, what will be the value? W into x is the load acting at the right side of this section. W into x. Now slide this section to point B. So shear force at point B. So that will be equal to W into x value will be 0. So it will be 0. Now slide the section to point A. So we will get shear force at point A. Shear force at point A, and that will be W into length, that is WL. Okay, so it is in Newton. So it is given Newton, so it will be Newton. If it is given in kg, so it will be in kg. Okay, so we have got, so with this information, we will draw the shear force diagram. So all the shear force are positive in nature. So we will draw the baseline, and at point B shear force is 0, mark the point, and at point A shear force is given by W into L. With some scale you measure this height, W into L, and just the variation, you can see the variation of shear force varies with x value. So that means linear. Variation is linear. So just it will be given by a straight line. Now, as it is positive, so we have drawn the diagram at the positive side, means above this line. This is the positive. Negative, it is below this line. So put this positive and put the hatching mark. So this is the shear force diagram for the cantilever beam, which is under UDL, under uniformly distributed load. Now we will go for bending moment diagram. So first find the equation of bending moment diagram at section XX. So bending moment diagram at section XX. Okay. So it is the moment of all the vertical forces, algebraic sum of moments of all the vertical forces acting to one side of the section. So one side we are considering right side. What is the load acting at the right side? That is W into x, where through its center of gravity it will act. So W into x load is acting through the center of this load, that is the center of gravity. So if this distance is x, so that means from the section, what is the distance where the total load is acting? That is x by 2 distance. Now bending moment at section XX is equal to load into distance, that is W into x by 2. Total load into the distance from the section. So that is Wx square by 2. Now slide the section to point B. So if we slide the section to point B, so bending moment at point B, that will be x value will be 0. So W into 0 square by 2, that is 0. And slide the section to point A. So that time we will get bending moment at point A. How much? W into L square by 2. So for bending moment, the moments will be negative. Okay. So with this information, we will draw the bending moment diagram. For drawing the bending moment diagram, draw a baseline first. First you draw a baseline. So this is the baseline. At this point bending moment is 0. At this point bending moment is WL square by 2. So we are writing here WL square by 2. And and the variation of bending moment is with x square. See, x value changes, so the bending moment will vary with x, means with x square. So that means the variation is parabolic variation. Parabolic variation. So variation is parabolic. Now with this information we will draw the bending moment diagram. So first you draw the baseline and then draw a parabolic curve from point A to B, where at point B it will be 0 and at point A it will be WL square by 2. So this curve is parabolic. So as we are drawing by freehand, so we will write here parabolic. Parabolic. Okay, and this is the negative moment, so we will write negative and put the hatching mark. Okay, so this will be the bending moment diagram for this kind of loading. Clear? Now next we will see the another one, that is, say the cantilever beam is subjected to uniformly distributed load plus combined with point load. Point load. So what should be the diagram for this kind of loading? So we will see the shear force and bending moment diagram when the cantilever beam is under point load plus uniformly distributed load for whole span of the beam. Now this is the beam, cantilever beam. Now this beam is under UDL for whole span of the beam, that is W Newton per meter length, as well as a point load capital W. Okay, capital W, it is acting at the free end. So this one is small w and this one is capital W. And say length of the beam is L. L is the length of the beam, and we are giving the name AB. Okay, consider a section XX here at a distance x from free end. At a distance x from free end. So we are considering a section XX. Now we are going to find what is the shear force at XX. So shear force at XX is given by algebraic sum of all vertical loads acting to one side of the section, the right side of this section, XX section. What is? So first capital W load is acting at the right side of the section, plus this uniformly distributed load is acting. What is the value of this uniformly distributed load? That is small w for x length. So small w into x. So this is the UDL part and this is the point load. So total vertical load acting right side of the section. That is the okay. Now slide the section to point B. So we will get shear force at point B. How much? When we will slide the section to point B, means one point left to point B, x value will be 0. So x value, if we put 0, it will only give W value. Okay. And now slide the section to point A. So it will give shear force at point A. So it will be, when we will slide the section, x value will be equal to L value. So instead of x we will write L. So capital W plus small w into L. So at fixed end will be capital W plus small w into L, and at free end it will be capital W. So with this information, all these shear force are positive. So we just draw a diagram under this load diagram. So this is the baseline. At this point, what is the value? W value, capital W. And at this point it is, say, W plus small w into L. So with some scale, you just mark these 2 points and the variation. So variation is variation of shear force. So from equation it is seen shear force varies with x. So that means variation is linear variation. Linear variations. So we will put or draw a straight line from these 2 points. So this will be the shear force diagram for this kind of loading on cantilever beam. So this is positive. So we will put positive here and put the hatching mark. Okay, this is the shear force diagram. Now we will move to find the bending moment diagram. So bending moment diagram, bending moment at section XX. So to find the bending moment at section XX, W will give a moment about this section, that is W into X, capital W into X, plus this is the UDL, total load for UDL is small w into X, and this distance is X by 2. So we can write small w into X by 2. Okay, so capital W into X plus small w into X square by 2. So this is the bending moment equation. Now slide the section to point B. So it will give bending moment at point B. Bending moment at point B. What will be the value? So at point B, X value will be 0. So it will give 0 value. Now slide the section to point A, where bending moment will be bending moment at point A, where X value will be L. So we can find capital W into L plus small w into L square by 2. And all these bending moment is negative. Okay. So now with this information we will draw the bending moment diagram. For drawing the bending moment diagram, first you draw the baseline. So baseline is drawn. Now at this point, what is the bending moment? At point B, bending moment is 0. At point A, bending moment, with some scale you measure this, capital W into L plus small w into L square by 2. So capital W into L plus half small w into L square. And the variation, we will see the variation in bending moment equation. So here you can see the maximum power of X is 2. So that means the variation is parabolic. Variation of bending moment with X distance is parabolic. Parabolic. So from this point you draw a parabola. So we are drawing by freehand. So we will write here this curve is parabolic curve. Parabolic. Okay, and here we have to give negative sign and put the hatching mark. So this is the bending moment diagram for this kind of loading. Now one more problem we will see, that is, say cantilever beam is subjected to UDL partly. What is UDL partly? So for whole length of the beam it is not acting, it is partly it is acting. So for this beam we will see the shear force and bending moment diagram. Now first we will draw the load diagram. So this is the load diagram, cantilever beam, say this is the cantilever beam, and this part it is loaded with, so the length from free end it is for A length, okay, the UDL acting, and the UDL value is W per meter length. Okay, W per meter length. Now give the name AB and total length of the beam is L. Now take a section here on UDL part which is at a distance x from free end, that is XX section at a distance x from free end which is inside this UDL part. Now we will see the shear force at XX. What is the shear force at XX? Algebraic sum of all vertical load acting to one side of the section. So we are considering right side of the section. So W into X is the load acting right side of XX section. Now, okay, take this point as C. Now slide the section to point B. So shear force at point B, X value will be 0, so it will give 0 value, W into 0. And slide the section to point C. So shear force at point C, so we will slide the section XX to point C, X value will become A. So that will be W into A. Variation is linear because it is varies with X. Variation is linear. So that means if we draw the part of this diagram, part of this shear force diagram, so this is the baseline. At this point it is 0. At this point, at point C, it is W into A. So this height with some scale measure it W into A. So we are writing here W into A. Okay. Now take another section, that is say YY section at a distance Y from free end. Y from free end. Now shear force at YY section. Shear force at YY section will be equal to the algebraic sum of all vertical loads acting to one side of the section, say right side of the section. What is that value? So it will be W into A value. So there is no variable. So that means no variation. So that means slide the section to point C. Slide the section to point C, shear force at point C will be W into A. And slide the section to point A, shear force at point A will be also W into A. Because there is no variable. In this equation there is no variable. So shear force will not vary. It will remain constant. So that means, so we can write, so here you take the measurement of W into A and just join this line. So this is the shear force diagram, and as it is a positive diagram, so put positive and put the hatching marks. Okay, so this is the shear force diagram for this beam and for this kind of loading. Now we will go for bending moment diagram. Now bending moment at section XX is equal to bending moment at section XX, that is moment of all vertical forces acting to one side of the beam, that is the right side of the beam. What is total load to the right side of this section? W into X, and the distance is X by 2 is equal to WX square by 2. So if we slide the section to point B, bending moment at point B will be X value is 0, so it will be 0. Now slide the section to point C, so we will get bending moment at section C, and that will be equal to, at C, what is the X value? A, that is W into A square by 2. Okay, now go to YY section, and with this, what is the variation? Variation is variation with X square, that is parabolic variation. Parabolic variation. Okay, and go to YY section. So we'll form the equation shear force at YY. What is shear force at YY section? So it is, see, at the right side of the section, total load acting is W into A. W into A. So we are writing W into A. and center of gravity load is exactly at the center. So we have to put this distance to get the moment. What is the distance? So this distance is a y and this distance is a by 2. So we write y minus a by 2. Y minus a by 2. That is the bending moment. See, this distance is y and this distance is a by 2. So y minus a by 2, it will give the bending moment at yy section. Wa into y minus a by 2. Now slide the section to point C. So it will give bending moment at point C. At C, bending moment at point C. So if we slide the section here, y value will be a. Bending moment at yy. Okay. W into a into y minus a by 2 and bending moment at C. So first we have got this one. Okay, no problem. Bending moment at C. So y value is a. So W a into a minus a by 2 and a minus a by 2 means a by 2. So it will be W a square by 2. So it will give the same value as we have got here. Okay. Now slide the section to point A. So bending moment at point A, and that will be, when we will slide the section to point A, y value will be L. So instead of y, we will write L. So that means WA into L minus a by 2. So this will be this value. So now with this information, we will draw the bending moment diagram. All the moments are negative. So draw the baseline. Then at this point, under this point C, how much it is? At point C, bending moment is W square by 2 with some scale W square by 2. And this side variation is parabolic. So you just put a parabolic curve. So we will write here parabolic. Okay. And this side. So from point C to A. So at point A, what is the value? WA into L minus a by 2. WA into L minus a by 2. So you measure this distance with some suitable scale and say this distance is coming up to this from here to here, and the variation, you can see the variation, it is varies with y. That means variation is linear variation, straight line variation. So from this point to this point, it will be a straight line because linear variation. And put this one as negative and put the hatching mark. So this will complete this bending moment diagram. Now in last video we have discussed the usefulness of this diagram. So at any point of the beam we need to find shear force or bending moment. So at this point we want to find what is the shear force. So at this point draw a vertical line. So this will be the shear force developed at this point, and this will be the bending moment developed at this point. If we want to find the shear force or bending moment at this point, so draw a vertical line on load diagram, from load diagram. So this will be the shear force acting at this point, and this will be the bending moment acting at this point. So this is the usefulness of this diagram. So hello friends, so that's all for today's video, and we will meet soon with a new video on this, that is shear force and bending moment diagram. And if this video is helpful to you, please subscribe, like and share the video. Thank you. We will meet you soon.